Hey guys, this is section 8.4, surface area of spheres, and we've talked about prisms and cylinders. Pyramids and cones. Our last shape that we'll talk about is the sphere. So a sphere is the set of all points in space equidistant, which means the same distance from a given point called the center. And so that's a similar definition to a circle. A circle is just a bunch of points that are the same distance away from the center, right? So that's what makes up a circle, and just put an infinite number of points. And when you put enough points, it starts to look like a curve, and it starts to look like actually a solid line, okay? Well, the same thing's true about a sphere, except three-dimensional. We don't just have a radius. Well, we still have a radius, but it's going every direction, not just two dimensions. And so the great circle separates the sphere into two congruent halves, and they're called hemispheres. So we have a semicircle is what half a circle is, and hemisphere is what half a sphere is. So when social studies, you talk about the northern and southern hemispheres, east and west hemispheres. That's a word you should be familiar with. So if you've ever had a baseball or a softball and kind of ripped or torn the covers off, or maybe you've used a baseball so much that that's just how it ends up after you hit it so much, the baseball is actually made up of what looks like four circles that have the same radius. And believe it or not, even though a sphere may be what you may think one of the most difficult shapes to find the surface area of, just because it looks so odd. I mean, you look at this picture and you're like, whoa, how do I do that? The surface area of a sphere is actually just that. It's four circles. And so the formula for the surface area of a sphere is 4 pi r squared. Probably the easiest surface area formula that we have. All right, so let's practice that. It's a pretty easy formula. Let's see what we can do here. For example A, we have a sphere with a radius of 8. So our surface area formula is 4 pi r squared. And so we're going to just plug in 8 for r. Now remember, you do have to square the 8 before you multiply it by 4 pi. And so that's going to be 4 times 64 times pi. And then 4 times 64 is 256 times pi. So if we had to write our answer in terms of pi, we would write 256 pi. If we want to round our answer, now it doesn't say what to round it to, let's just say to the nearest hundredth, we would times 256 by 3.14, or you can use the pi button. I'm going to use 3.14, and that should give us 803.84 inches squared. It's still area, so we still do inches squared. Spheres don't really have a different shape. Like, there's many different kinds of pyramids, prisms, even cylinders can look different, and cones, but a sphere is always the same shape. The only thing you can change on it is the size of the radius. Or maybe they give you the diameter. That's okay. That just means we have a radius of 20 here. So if the radius equals 20, then we're going to do S equals 4 pi r squared, or 4 times pi 20 squared. And then 20 squared is 400. 400 times 4 is 1600. And 1600 times 3.14 is 5024. And again, I used 3.14, not the pi button when I did mine, but you're welcome to use the pi button. What I've shown right here, and actually what I'm highlighting right here, is the least amount of work that you would need to show. Because the formula does not have a plus sign in it, you can actually get away with doing it all at one time in your calculator. Just make sure, if you don't have a scientific calculator, that you're squaring the 20 first to get 400, and then timesing by 4, and then by 3.14. So 5,024 square feet. So this next one says, Earth is not a perfect sphere, but it has been molded by gravitational forces into a spherical shape. Earth has a diameter of about 7,926 miles. Find its surface area. So a realistic problem here. How much surface area is on the Earth? Now remember, it's not all inhabitable. We have oceans make up most of the Earth, but we can still find its surface area. So this isn't just the land. This is the entire Earth, including the water. And so if it has a diameter of 7,926, we would want to divide this by 2 to find the radius. and that's going to give us 3,963 is what the radius is. So surface area equals 4 times pi r squared. 3,963 squared is, gosh, that's a big number. That's a 15,705,369. You should hopefully are following along with your own calculator. I'm going to times that by 4 now, and then times it by 3.14. Again, I'm just going to use 3.14 instead of the pi button. That's okay if you use the pi button. And that's going to give us an answer. Let me write it all down before I figure out where I need to put my commas. 197259434.6. So let's figure out what this is. Make sure I didn't lose any numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's put my commas in here. And that means the surface area of the Earth is 197,259,434.6, and that would be square miles. Square miles. That's a lot of surface area. Again, not all of it is inhabitable. And so the next video I have for you guys, I'm going to put a video in my own video, is a video that explains why we're not able to get an accurate map. So if I go back to that baseball that we looked at, even though the surface area is 4 pi r squared, so 4 times the area of a circle, the shape itself is not very good to use and make flatten out. It's very hard to flatten out a sphere, and so this next video is going to go over that.
All right, here we go. If I want to turn this globe into a flat map, I'm going to have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa. By a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we will end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
Okay, the Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
So if you want to see a map that more accurately displays land area, you can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted. Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up. But on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Winkle triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer. If you yourself want to poke fun at the Mercator projection, you can do so by going to thetruesizeof.com, which is a fun tool that allows you to drag around whatever country you want around the map and see how it is distorted depending on where it is. I also want to say a big thanks to
So I'd encourage you to go to that website, thetruesizeof.com. That's kind of a fun to play around with that, and you can see just the farther the country is away from the equator, the more distorted it is on the Mercator projection. But there's no perfect way to do a map because it's really just difficult. You think that since it's so difficult to create a net of a sphere, you'll remember the sphere is the only shape that we didn't actually do the net of in our net slab. You'd think the surface area formula would be harder to use, but it's actually one of the easiest ones, 4 pi r squared. All right, let's have some fun now and do some more interesting problems with spheres. This one wants us to find the surface area of a sphere, but instead of giving us the radius, which we need, it's giving us the circumference. And so I have to think about this for a second. How am I going to find the radius of this sphere if they're giving me the circumference? Well, remember, the circumference formula is pi times d. So that would make the 12 then the diameter. And if 12 is the diameter, that would make the radius 6. So just an interesting way of getting us to our radius. So 4 times pi r squared. 6 squared is 36. 36 times 4 is 144. I'm going to use 3.14 again and get 452.16 feet squared. Okay. The next one here wants us to find the diameter, not the surface area, but the diameter. So we're going to need to work backwards. And so if my surface area formula is 4 pi r squared, I'm going to plug in, instead of for r, I'm going to plug in for s. They want me to plug in 20.25 pi for the surface area. Just plugging that in for s right here. And then I'm going to solve this equation. We've done a couple like this, where we had problems like this, where we have to let's see, get rid of the pi's on each side. We can divide both sides by pi and get rid of oops, not the radius, the pi on that side. And then I would divide both sides by 4. So not just by pi, but by 4. And 20.25 divided by 4 is 5.0625. Don't round that yet. And of course, that 4 is gone, so equals r squared. And then what I'll do is I'll find the square root. That would be the opposite since I'm working backwards. I'm going to find the square root of both sides so I can just find the radius. And so I'm going to square root my previous answer. Remember, you can find your square root button on your calculator. And that's going to give us a radius of 2.25 centimeters. But this problem wanted us to find the diameter. And so if I double that and times that by 2, that gives us a diameter of 4.5 centimeters. So that's how I can work backwards to find either the radius or, in this case, the diameter of a sphere. And last but not least, we have a couple complex shapes, composite shapes. This one is a hemisphere, and we need to find the surface area of this hemisphere. Now, our full sphere formula would be 4 pi r squared, but because this is a hemisphere, I'm going to cut that in half and make this 2 pi r squared. However, the 2 pi r squared is going to give me the curvy circle on the outside, okay, the curved part of the circle on the outside. But when I split a sphere in half and make it a hemisphere, what I'm actually doing is taking a shape that has one surface, and when I split it in half, I actually create a whole nother surface, because now this, what we call the great circle, is now on the bottom of that sphere. And so it has an area of pi r squared, so I'm going to add another pi r squared to the 2 pi r squared, making that 3 pi r squared. That was a mouthful. So when you cut a sphere in half, it does take half of the surface area away, but it also introduces this surface that wasn't there before on the bottom of the hemisphere, and so I have to add that pi r squared in, and so our surface area is now going to be 3 pi r squared. Now let me erase all this because I need to know what my radius is. It's giving me the diameter of 12, and that would make the radius then a 6. So 3 times pi 6 squared. We said 6 squared is 36. 36 times 3 is 108, and I'm going to times that by 3.14 to get 339.12 inches squared. And our last one is this weird looking shape, looks like a pill, where we have a cylinder with 2 hemispheres. And I'm finding the surface area of this shape. And so what they've done is they've cut my sphere in half and put it on each side. And so I'm still going to use my full sphere formula because the entire sphere is still visible. It's just been split in half. And so we're going to do 4 pi r squared, just the normal formula. And then I have this cylinder here in the middle. But the 2 circles on either end of the cylinder, this one here and this one here, are covered up by the hemispheres. So I don't want to include them. So remember, the formula for a cylinder is 2b plus ch. Well, if both of my circles are missing, I'm just going to scratch this out and find the lateral area of just the rectangle part, right? If I were to unroll this, and that's the ch part. So that's all I want to add here. And so plus ch, except c, I'm going to go ahead and replace that. That's circumference. So pi times d makes that pi times 12. And then the height of that rectangle is 14. So I'm just using this part of the formula because the 2 circles are covered up by the hemispheres. So on the left side, I should have probably went ahead and plugged 6 in for the radius. Pi times, 6 squared, we'll start with that. 36 times 4 times 3.14 is going to give, oh, don't even times by 3.14 yet. Let's write this in terms of pi first. 144 pi. Saves me some time if I do that. And then 12 times 14 is 168 pi, and then add that to the 144 to get 312 pi, and then now I can multiply by pi at the end. So times by 3.14 to get 979.68 meters squared. So we can still use the formulas from our previous sections to find the formula or find the surface area of these composite shapes. And we'll do more of that on Thursday when you come back to review for Friday's quiz.